Enthalpy is defined as a thermodynamic state function, designated by the letter H, that consists of the internal energy of the system plus the product of pressure and volume of the system. Since U, P and V are all functions of the state of the thermodynamic system, enthalpy is a state function. The unit of measurement for enthalpy in the international system of units is the joule, but other historical, conventional units are still in use, such as the British thermal unit and the calorie. The enthalpy is the preferred expression of system energy changes in many chemical, biological, and physical measurements at constant pressure, because it simplifies the description of energy transfer. At constant pressure, the enthalpy change equals the energy transferred from the environment through heating or work other than expansion work. The total enthalpy, H, of a system cannot be measured directly. The same situation exists in classical mechanics. Only a change or difference in energy carries physical meaning. Enthalpy itself is a thermodynamic potential, so in order to measure the enthalpy of a system, we must refer to a defined reference point. Therefore what we measure is the change in enthalpy, delta H. The delta H is a positive change in endothermic reactions, and negative in heat-releasing exothermic processes. For processes under constant pressure, delta H is equal to the change in the internal energy of the system, plus the pressure-volume work that the system has done on its surroundings. This means that the change in enthalpy under such conditions is the heat absorbed by the material through a chemical reaction or by external heat transfer. Enthalpies for chemical substances at constant pressure assume standard state, most commonly 1 bar pressure. Standard state does not, strictly speaking, specify a temperature, but expressions for enthalpy generally reference the standard heat of formation at 25 degrees Celsius. Enthalpy of ideal gases and incompressible solids and liquids does not depend on pressure, unlike entropy and Gibbs energy. Real materials at common temperatures and pressures usually closely approximate this behavior, which greatly simplifies enthalpy calculation and use in practical designs and analyses. Origins. The word enthalpy is based on the Greek enthalpein, which means to warm in. It comes from the classical Greek prefix nu-en, meaning to put into, and the verb theta alpha lambda pi epsilon iota nu thalpon, meaning to heat. The word enthalpy is often incorrectly attributed to Benoit Paul-Émile Clapeyron and Rudolf Clauses through the 1850 publication of their Clauses-Clapeyron relation. This misconception was popularized by the 1927 publication of the Mollier steam tables and diagrams. However, neither the concept, the word, nor the symbol for enthalpy existed until well after Clapeyron's death. The earliest writings to contain the concept of enthalpy did not appear until 1875, when Josiah Willard Gibbs introduced a heat function for constant pressure. However, Gibbs did not use the word enthalpy in his writings. The actual word first appears in the scientific literature in a 1909 publication by J. P. Dalton. According to that publication, Heike Kamerlingh-Onnes actually coined the word. Over the years, many different symbols were used to denote enthalpy. It was not until 1922 that Alfred W. Porter proposed the symbol H as the accepted standard, thus finalizing the terminology still in use today. Formal definition. The enthalpy of a homogeneous system is defined as where H is the enthalpy of the system, U is the internal energy of the system, P is the pressure of the system, V is the volume of the system. The enthalpy is an extensive property. This means that, for homogeneous systems, the enthalpy is proportional to the size of the system. It is convenient to introduce the specific enthalpy H equals H per meter, where m is the mass of the system, or the molar enthalpy Hm equals Hn, where n is the number of moles. For inhomogeneous systems, the enthalpy is the sum of the enthalpies of the composing subsystems, where the label K refers to the various subsystems. In case of continuously varying PT and/or composition, the summation becomes an integral, where ρ is the density. The enthalpy of homogeneous systems can be viewed as function h of the entropy S and the pressure P, and a differential relation for it can be derived as follows. We start from the first law of thermodynamics for closed systems for an infinitesimal process. Here, delta Q is a small amount of heat added to the system, and delta W a small amount of work performed by the system. In a homogeneous system only reversible processes can take place, so the second law of thermodynamics gives delta Q equals TdS, with T the absolute temperature of the system. Furthermore, if only PV work is done, delta W equals PdV. As a result, adding d to both sides of this expression gives also other expressions. The above expression of dH in terms of entropy and pressure may be unfamiliar to some readers. However, there are expressions in terms of more familiar variables such as temperature and pressure. Here Cp is the heat capacity at constant pressure, and alpha is the coefficient of thermal expansion. With this expression one can, in principle, determine the enthalpy if Cp and V are known as functions of P and T. Notice that for an ideal gas, so that in a more general form, the first law describes the internal energy with additional terms involving the chemical potential and the number of particles of various types. The differential statement for dH then becomes where μI is the chemical potential per particle for an I-type particle, and Ni is the number of such particles. The last term can also be written as μIdNi or as μIdMi. Physical interpretation. The U term can be interpreted as the energy required to create the system, and the PV term as the energy that would be required to make room for the system if the pressure of the environment remained constant. When a system, for example, n moles of a gas of volume 5 at pressure P and temperature T, is created or brought to its present state from absolute zero, energy must be supplied equal to its internal energy U plus PV, where PV is the work done in pushing against the ambient pressure. In basic physics and statistical mechanics it may be more interesting to study the internal properties of the system and therefore the internal energy is used. In basic chemistry, experiments are often conducted at constant atmospheric pressure, and the pressure-volume work represents an energy exchange with the atmosphere that cannot be accessed or controlled, so that delta H is the expression chosen for the heat of reaction. Relationship to heat. In order to discuss the relation between the enthalpy increase and heat supply, we return to the first law for closed systems. Do equals delta Q minus delta W. We apply it to the special case with a uniform pressure at the surface. In this case the work term can be split into two contributions, the so-called PV work, given by PDV, and all other types of work delta W, such as by a shaft or by electromagnetic interaction. So we write delta W equals PDV plus delta W. In this case the first law reads, or from this relation we see that the increase in enthalpy of a system is equal to the added heat, provided that the system is under constant pressure and that the only work done by the system is expansion work. Applications. In thermodynamics, one can calculate enthalpy by determining the requirements for creating a system from nothingness. The mechanical work required, PV, differs based upon the conditions that obtain during the creation of the thermodynamic system. Energy must be supplied to remove particles from the surroundings to make space for the creation of the system. Assuming that the pressure P remains constant, this is the PV term. The supplied energy must also provide the change in internal energy, U, which includes activation energies, ionization energies, mixing energies, vaporization energies, chemical bond energies, and so forth. Together, these constitute the change in the enthalpy U plus PV. For systems at constant pressure, with no external work done other than the PV work, the change in enthalpy is the heat received by the system. For a simple system, with a constant number of particles, the difference in enthalpy is the maximum amount of thermal energy derivable from a thermodynamic process in which the pressure is held constant. Heat of reaction. The total enthalpy of a system cannot be measured directly. The enthalpy change of a system is measured instead. Enthalpy change is defined by the following equation. Whereas the enthalpy change is the final enthalpy of the system, is the initial enthalpy of the system. For an exothermic reaction at constant pressure, the system's change in enthalpy equals the energy released in the reaction, including the energy retained in the system and lost through expansion against its surroundings. In a similar manner, for an endothermic reaction, the system's change in enthalpy is equal to the energy absorbed in the reaction, including the energy lost by the system and gained from compression from its surroundings. A relatively easy way to determine whether or not a reaction is exothermic or endothermic is to determine the sign of delta H. If delta H is positive, the reaction is endothermic. That is, heat is absorbed by the system due to the products of the reaction having a greater enthalpy than the reactants. On the other hand, if delta H is negative, the reaction is exothermic. That is, the overall decrease in enthalpy is achieved by the generation of heat. Specific enthalpy. The specific enthalpy of a uniform system is defined as H equals H per meter, where m is the mass of the system. The SI unit for specific enthalpy is joule per kilogram. It can be expressed in other specific quantities by H equals U plus PV, where U is the specific internal energy, P is the pressure, and V is specific volume, which is equal to 1 ρ, where ρ is the density. Enthalpy changes. An enthalpy change describes the change in enthalpy observed in the constituents of a thermodynamic system when undergoing a transformation or chemical reaction. It is the difference between the enthalpy after the process has completed, i.e., the enthalpy of the products, and the initial enthalpy of the system, i.e., the reactants. These processes are reversible, and the enthalpy for the reverse process is the negative value of the forward change. A common standard enthalpy change is the enthalpy of formation, which has been determined for a large number of substances. Enthalpy changes are routinely measured and compiled in chemical and physical reference works, such as the CRC Handbook of Chemistry and Physics. The following is a selection of enthalpy changes commonly recognized in thermodynamics. When used in these recognized terms, the qualifier change is usually dropped and the property is simply termed enthalpy of process. Since these properties are often used as reference values, it is very common to quote them for a standardized set of environmental parameters, or standard conditions, including a temperature of 25 degrees Celsius or 298 K, a pressure of 1 atmosphere, a concentration of 1.0 m when the element or compound is present in solution, elements or compounds in their normal physical states, i.e., standard state. For such standardized values, the name of the enthalpy is commonly prefixed with the term standard, e.g., standard enthalpy of formation. Chemical properties. Enthalpy of reaction, defined as the enthalpy change observed in a constituent of a thermodynamic system when 1 mole of substance reacts completely. Enthalpy of formation, defined as the enthalpy change observed in a constituent of a thermodynamic system when 1 mole of a compound is formed from its elementary antecedents. Enthalpy of combustion, defined as the enthalpy change observed in a constituent of a thermodynamic system when 1 mole of a substance burns completely with oxygen. Enthalpy of hydrogenation, defined as the enthalpy change observed in a constituent of a thermodynamic system when 1 mole of an unsaturated compound reacts completely with an excessive hydrogen to form a saturated compound. Enthalpy of atomization, defined as the enthalpy change required to atomize 1 mole of compound completely. Enthalpy of neutralization, defined as the enthalpy change observed in a constituent of a thermodynamic system when 1 mole of water is formed when an acid and a base react. Standard enthalpy of solution, defined as the enthalpy change observed in a constituent of a thermodynamic system when 1 mole of a solute is dissolved completely in an excessive solvent, so that the solution is at infinite dilution. Standard enthalpy of denaturation, defined as the enthalpy change required to denature 1 mole of compound. Enthalpy of hydration, defined as the enthalpy change observed when 1 mole of gaseous ions are completely dissolved in water, forming 1 mole of aqueous ions. Physical properties. Enthalpy of vaporization, defined as the enthalpy change required to completely change the state of 1 mole of substance between liquid and gaseous states. Enthalpy of sublimation, defined as the enthalpy change required to completely change the state of 1 mole of substance between solid and gaseous states. Lattice enthalpy, defined as the energy required to separate 1 mole of an ionic compound into separated gaseous ions to an infinite distance apart. Enthalpy of mixing, defined as the enthalpy change upon mixing of two chemical substances. Open systems. In thermodynamic open systems, matter may flow in and out of the system boundaries. The first law of thermodynamics for open systems states, the increase in the internal energy of a system is equal to the amount of energy added to the system by matter flowing in and by heating, minus the amount lost by matter flowing out and in the form of work done by the system, where is the average internal energy entering the system, and is the average internal energy leaving the system. The region of space enclosed by the boundaries of the open system is usually called a control volume, and it may or may not correspond to physical walls. If we choose the shape of the control volume such that all flow in or out occurs perpendicular to its surface, then the flow of matter into the system performs work as if it were a piston of fluid pushing mass into the system, and the system performs work on the flow of matter out as if it were driving a piston of fluid. There are then two types of work performed: flow work described above, which is performed on the fluid, and shaft work, which may be performed on some mechanical device. These two types of work are expressed in the equation. Substitution into the equation above for the control volume CV yields. If we allow also the system boundary to move, we get a rather general form of the first law for open systems. In terms of time derivatives it reads, with sums over the various places k where heat is supplied, matter flows into the system, and boundaries are moving. The terms represent enthalpy flows, which can be written as with the mass flow and the molar flow at position k respectively. The term dvk dt represents the rate of change of the system volume at position k that results in PV power done by the system. The parameter P represents all other forms of power done by the system such as shaft power, but it can also be e.g., electric power produced by an electrical power plant. Note that the previous expression holds true only if the kinetic energy flow rate is conserved between system inlet and outlet. Otherwise, it has to be included in the enthalpy balance. During steady-state operation of a device, the average dt may be set equal to 0. This yields a useful expression for the average power generation for these devices in the absence of chemical reactions, where the angle brackets denote time averages. The technical importance of the enthalpy is directly related to its presence in the first law for open systems, as formulated above.